Well, hello. I don't have any visitors today, but that's probably because of midterms and people are all in the throes of doing midterms and stuff and things and stuff. That's okay. Doesn't matter. The main thing is that this is recorded, and so you can tune into it at any time. What we're going to cover now in the second half of the course is the stuff that isn't necessarily compression. So we'll leave that kind of behind, and we're going to focus now on today's features, the features and benefits found on today's digital hearing aids. That would be the general gist and drive and point of this particular unit, Unit 5, in which we will spend a couple of weeks on this Unit 5. Well, let's begin by looking at our notes over here. I will share screen, and we'll take a look-see at what we've got. Okay, good at the notes. There we are. Digital hearing aids, channels, feedback reduction, compression and expansion. Yikes, expansion, the opposite of compression. Let's read. Let us read. Won't that be special? Here we are. To appreciate digital hearing aids, we've got to understand their analog forebears, and that's what we did in the first half of the class. Analog hearing aids had either one type of compression or another type. In other words, they were either output limiting compression or WDRC, or WDRC with bill, or WDRC with till, or WDRC with batil, both. And I always call that the golden age of compression, and that's why I draw it right here like this. Because there was the good old days. What I mean by that is those were the times when people had to know their compression types, because the hearing aid was either one type or another type, and if you ordered the wrong hearing aid, you ordered the wrong one. You had to send it back to the manufacturer and get another one, okay? Hearing aids were analog. They just had hardware, no software. Today's hearing aids are digital, and so they can combine all types of compression. You can make the hearing aid output limiting. You can make the hearing aid WDRC. You can make the hearing aid have both, okay? In fact, that's what most of them do. So we'll talk much more about that as we go. Digital hearing aids began as digital imitations of analog hearing aids. Very important sentence to put a star beside. Compression, multi-channel, programmability of the high-end analog hearing aids of 1995, 1996, all of these were imitated in 1997 with the advent of digital hearing aids. Today's digital hearing aids now combine all sorts of compression types together. Ratios, knee points, all can be adjusted by the fitting software, and the complexity of any one digital hearing aid is now overwhelming. Digital algorithms, read commands, combine compression, directionality of the microphone, digital noise reduction, feedback reduction. So many adjustments are possible in each channel separately. So if you have a 20-channel hearing aid, you have 20 times all this. So therefore, it's impossible for clinicians to manually adjust all parameters for one hearing loss. Fitting software thus becomes king. Manufacturers fitting software that you were shown in your labs just on the weekend, programming the hearing aids. Excuse me, off-bounds parameter settings are deliberately prevented by the software. You'll recall a couple of weeks ago when I was talking about adaptive compression and average compression, we were talking about attack release times, and I was saying to you, under dynamic aspects of compression, I was saying to you, don't mess with those things on the software. In fact, a lot of the times the software won't even let you. They're off bounds. You'll screw it up. So anyway, the trouble is with the software is that you don't always know exactly what changes occurred. Psychosocial answers to various kinds of questions now determine the settings. For example, and I write this in my textbook too, I do it on purpose just to be funny. So, does your client have trouble hearing in church at a 45-degree angle every second Sunday? If so, hit this button. And then something happens, but you don't really know what it did. Okay? Clinicians all too often simply hit the quick fit button to adjust settings for anyone's hearing loss. Predictions offered by the fitting software are based on averages. You need the software. You gotta have the software or you're screwed. You can't even begin because the complexity is overwhelming. But never think that your fitting is done just because you fit with the software. You need to verify and prove, are you getting what the software said you'd get? And that's what you will be learning in 250 next semester, real ear measurement. Anyway, subsequent real ear probe tube measures show oftentimes different results from the predictions given in the manufacturer fitting software. By this I mean, when you pull up, for example, Phonak, Sparky, Unitron, whatever. Why is this weird eyebrow sticks up like that? You know why? It's because when I was 6 years old, I fell off of a toboggan. We were going down a hill, and I cut myself on some ice. Anyway, that was on a need-to-know basis. You needed to know that in order to pass the course. So, at any rate, what I'm saying to you is you go onto the software. You pick any software. You're going to choose your hearing aid. You have entered into NOAA, the client's hearing loss, address, name, all the client data. Then you go to the manufacturer you want. You choose the hearing aid you want. Then you program the hearing aid according to your hearing loss that you entered and the fitting method that you chose. Maybe it was the manufacturer's proprietary fitting method. You learned fitting methods in 150. Maybe it was the NAL fitting method. Maybe it was the DSL fitting method. I don't know, whatever fitting method you choose, the hearing loss and fitting method are married together to give you the frequency response of the hearing aid and all the compression characteristics of the hearing aid. Then you save the settings onto the programmed hearing aid and fit the client with the hearing aid. Great, but your job isn't really done there. You should always prove by putting a probe tube in the ear canal and taking the hearing aid that's been pre-programmed that way, and then enter the fitting method into the real ear system, the same fitting method, the same hearing loss. Now, in a lot of real ear systems, this is connected automatically with NOAA. So oftentimes NOAA will save the audiogram, and NOAA will also save the audiogram for the real ear measurement, which is great, and you don't have to enter it twice. Anyway, so you've programmed the hearing aid according to the hearing loss along with the fitting method that you chose, saved the settings, and now you're doing real ear. And are you getting what the software said you'd get? Remember, the software is based on averages. You doing real ear are proving, okay, what's it doing on individual X as opposed to individual Y, because they both have different ear canals. So what's happening with the hearing aid in all reality? So the software predicts and paints a picture, and you know what? More than 50–60% of HISs out there stop there and do the fitting. Less than half follow up with real ear. And that's almost a crime, because that's like me saying to you, yeah, I think you got cancer, without taking a biopsy to prove it. You need to prove, are you getting what the software said you'd get? And your method of verification is usually real ear measurement. Okay, so there's that sermon. All right? The other thing is this line. Far too many clinicians don't actually take the time to listen to the hearing aid themselves. There's no better analyzer than an intact cochlea. Just thought I'd tell you that. So now let's move on to our next topic concerning analog versus digital. And let's look at a picture here so you can see. Analog versus digital hearing aid circuits. Look at the top. The top is showing you sound coming into a mic. Now, there's nothing digital about the mic. A mic is a mic is a mic. A mic is a transducer. It changes sound waves into electricity. So, then you've got the amplifier. Now, this is an analog hearing aid. So your battery is adding electricity. Your amplifier is increasing the gain according to how you set things. And then that electricity is sent to the receiver. Now notice, here's your acoustic, here's your sound wave, here's your electrical wave, and now you've got a bigger electrical wave, and that's transduced by the receiver or speaker back into a bigger sound wave. So smaller wave into a more bigger one, okay? That would be analog. When you look at digital, you have one more transduction. The mic isn't much different. Changes sound into electricity. The electricity here is sent to an A to D converter, analog to digital converter. That means this electrical current is changed into digits, a series of zeros and ones. And when you've got math, you can do anything you want. Everything is now formulas. Everything's equations. It's statistics. It's math. And so what you're doing is the math and the number crunching is taking place in the DSP, the digital signal processor. That's the heart of the hearing aid. Once that's all done, that gets sent to a D to A converter, digital back to analog converter. So now the reorganized numbers are changed back into electricity, and that electricity is sent to the receiver, which, just like in the analog hearing aid, transduces the electricity back into sound. So back up into analog, instead of sound into electricity back into sound, it's sound into electricity into numbers into electricity into sound. That's the general gist about digital hearing aids. Now, when you're talking digital hearing aids, you're looking at something called sampling and quantization. Well, just to make things weird, we're not engineers, so we're not going to concentrate on this a lot, but just kind of humor me, follow this. Here's a sound wave in red. Okay, that's the analog sound wave. That's the, and then you can call that the analog electrical wave, because it's, remember, sound into electricity. So now you've got the electrical wave. Digital processing takes samples of these electrical waves. So what's missing is the stuff between the dots. Okay? Anyway, the dots are assigned an intensity value. This is intensity. This is your sampling rate. So the dots are assigned a value. This one is going to be more, is going to be either here. This one here is closer to 0.6. So I guess it's going to be assigned here. This one's a little bit closer to 0.8 than it is to 6. So boom, it's going to be assigned there. This one's a little bit closer to 0.8. So boom, it'll get that assigned. These three will all be given a similar assignment of value. So your samples are assigned values. So now if you look at the right, and I'll blow this up to make it more bigger, okay, the red is your wave, and the white is your digital representation of that wave. This is why the purists in the music industry don't always like digital, because they go, oh, look what's missing. If you really want the sound, you got to go back to analog. This is why people are going back to turntables, back to records, back to needles on records. Okay? The purists are saying the white wave has lots of little jiggles and steps in it, and it's made by sampling and quantization, such as is done in digital processing. But the real audiophile, the real purist, is always going to stick to Snickers, is always going to stick to the analog. Now, there's truth and there's falseness in that, okay? Because in general, sampling and quantization have gotten so good today that the white waves have way fewer steps, and they look almost just as faithful as the red wave. We've improved our sampling and quantization quite a bit. Anyway, I will escape out of here and read our writing. Analog versus digital. Analog current is a continuous imitation of the sound waves. The current is a continuous imitation of the sound wave. Continuous imitation. The electrical current is analogous to the sound wave. It's the same. That's why they called it analog. Back to here. Sound is changed into electricity. The electricity is amplified. Electricity changed back into sound. The electrical current is analogous to the sound waves that come into the aid. Let me just tell you a story here about record players that are coming back in. You know, the platters that spin. They were in when I was young. They're coming back in now. They're analog. How come? Because the needle on the record's turning, and the needle is dragging on the record. And if you look closely at the actual plastic record, you'll see tiny little grooves. And if you look closely at those tiny little grooves, and I'll draw you a round record here, it's got thousands and thousands and thousands and thousands and thousands of these little grooves. Okay? And the needle starts here, and then over the course of about a half an hour, it eventually ends here, and now you're done the record, and it's going, you have to shut off the record because you've played all the songs. So those grooves are way more than I'm drawing here. There's thousands and thousands and thousands of them. They're really, 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 really thin. Now, in each of those grooves, if I draw a cross section, looks like the letter V. Okay, each groove, and the needle drags, the end of the needle drags in the groove. Okay, so think of this as the end of the needle, okay, and it's touching the sides of the groove. Now, in the groove are these little indentation markers, kind of like this. And so the needle is dragging along those little bumps, okay? Now, what happens is when they made the record, someone was singing into a mic, and the mic changed the sound into electricity, and they had a soft wax platter, and the electricity made little wiggles because it was analogous to the sound waves, and it created analogous little wiggles inside the grooves, and those were let to harden. And so now when you played a needle like that, the needle is going and it's making an electrical current in the arm of the record player. Here's the needle, and it's going, it's got these little tiny movements, and those little tiny movements are given analogous electrical current. So the electrical current is analogous to the of the needle. So the electrical current looks just like the wiggles of the needle. The sound is amplified, and it comes out of the speakers, and the speakers are going analogously to the electrical current. Everything is preserved from the wiggle of the needle in the record to the electrical current to the physical wiggle of the speaker that produces the sound that you're hearing. So the little bumps in the groove are what you're going to hear Ella Fitzgerald or Def Leppard or Who knows? Whatever you're listening to, okay, is going to be played through the speaker. It all depended on the shape of those weird little bumps in the grooves of the record. That's what I mean by analogous. Okay, that's why everything that isn't digital is called analog. And analog just means this thing only had hardware. Just like a record player. It has the hardware of the needle, the arm of the record, of the needle that holds the needle, the spin of the platter, and the amplifier. There's nothing digital about it. It's all hardware. And that's how hearing aids work too. Mic, amp, receiver, hardware. Like my computer. Monitor, mouse, keyboard, CPU, all of that's hardware. The software is the apps. It's Microsoft Word, it's PDF, it's PowerPoint, it's Excel. All that's software. And that's all digits. So as soon as you got into digital, you are leaving that analog world a bit behind. And it's not that all analog is bad, because it isn't. But the genius of digital is that because you've changed things into math, you can manipulate numbers any way you want. And so digital hearing aids have way more fitting flexibility than analog hearing aids. Way more. So with analog, I could kind of do this. I could have a frequency response. I like drawing like this. It's kind of fun to do this. So an analog hearing aid might have a frequency response that does this. Okay, if this is frequency, and this is gain, let's say. Okay, and with an analog hearing aid, I could always cut the lows, or cut the lows. I could do that if I wanted to. And you could do the same with the treble. But digital, because you've got so many channels, I can raise or lower these like fingers. And the more channels I have, the more I can deliberately sculpt and shape my frequency response. So you've got way more fitting flexibility with digital. So that's a big advantage of digital. So digital, the digits are discrete representations of the sound. Sound is changed into electricity, electricity into digits. The digits are manipulated. Digits are changed back into electricity, and the electricity is now back into sound. In digital hearing aids, we use digital signal processing. And that's the picture that you're seeing here. DSP is the heart of the hearing aid. So know what A to D is, know what DSP is, know what D to A is, because all digital hearing aids have it. Don't worry so much about sampling and quantization. That's kind of more the story behind the scenes. I'm never going to ask about that. Here, when you've got lots of frequencies or bands, look what you can do. I can leave these ones low. I can increase these more, increase these, take away these, and I can literally sculpt or shape the frequency response of a hearing aid in far more exquisite detail than I could otherwise. So sampling rate, quantization, I just used that to tell a story. Now we move on our way down toward the bottom of page 1. Many bands, channels to enhance fitting flexibility. And that was this slide here. Now this one's got, I don't know how many, let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's a fictitious hearing aid. I made it up. It might have more, it might have fewer. Whatever. Go to your notes. The first digital hearing aid was the Widex Senso. And it had 3 bands. So it was a real, you adjusted things this way. And I'll just erase this, and I'll erase this. let's see, I'll take this one here away. You kind of did this. I'll take this. I'm just drawing something. Hang on a second. I'll be right there. Okay. You ended up having something like this. Whoops. Stop share. You had 3 fat ones. Okay. That's better than having 2. You had better fitting flexibility than just 2 channels, so it's more better. You had 3. Okay. Digital hearing aids. Widex Senso. Remember that one. First digital hearing aid, 1997. Each band was a channel. What does that mean? Let's read here on the bottom. Bands versus channels. Industry convention. In digital hearing aids, a channel is a band if only the gain is adjustable. Okay? But if more than gain is adjustable, in other words, if digital noise reduction is part of it, and directional mic behavior is part of it, and compression is part of it, and all that, if more is adjusted in a particular band, then it's called a channel. Okay? So you could have lots that can be adjusted. Knee points, ratios, directionality, noise reduction, feedback reduction, all kinds of stuff. The second digital hearing aid was called Otakon Digifocus, and I'll draw you that one too now, because that helps to discern the difference between bands versus channels. Here we go. It had 1, 2, 3, 4, 5, 6, and 7. We'll make this nice and neat so that we can't say it's a scrawled Ted Venema mess. Okay? All right. So it had 7 bands. I'll show this again here just so we all have this clear. 7 bands, okay? And then the bottom 4 on the left was called channel 1. And the top 3 on the right was called channel 2. So here we go. Channel 1, the bottom 4 bands. Channel 2, the higher frequency, 3 bands. And what did they do in here? Well, you could not only adjust the gain, but you could adjust the compression. This was Bill, bass increase at low levels. So you did all kinds of weird things in here. So this was a group of bands that shared a digital algorithm. In each band, you could only adjust the gain, but then they could lump together to produce a channel where stuff other than gain could be adjusted. And then channel 2 was the collection of the highest frequency 3 channels. So the gain was individually adjustable in each band, and then they were also lumped together as channel 2 when they shared a different kind of behavior, where you could adjust something other than just the gain in those 3 channels. Okay? Anyway, just to kind of highlight the difference between band and channels. Today's digital hearing aids, basically the bands are the channels. Why? Because you can adjust gain and other stuff in the bands. Therefore, it's no longer just a band. Okay, Otakon Digifocus had 7 bands. First 3 comprise the low frequency, and the next 4 comprise the high. Okay, I drew it a little backwards. Anyway, you know what I mean. Then came Siemens Prisma. It had 4 bands and channels. And then came Resound. It had 14. And then now you've got all kinds of permutations out there today. Okay, look where we've come so far. There used to be a hearing aid, and I'm not 100% sure if it still exists. It may no longer exist, okay? But it was produced by Bernafon, and it was called the Symbiote. And the Symbiote was what they called a channel-free digital hearing aid. It didn't use channels. It acted like an analog hearing aid, but it was channel-free. People said it sounded very, very nice. They quite liked it. But all it did was instantly and constantly update its frequency response. Instead of by raising or lowering individual little fingers, I love that when the PowerPoint just disappears. It's just weird, okay? Anyway, instead of raising or lowering like little fingers, this one here all acted at all frequencies changed completely the bass gain and treble gain as it instantly updated itself in time. So it was said to work in the time domain as opposed to in the frequency domain. Don't worry, I won't ever ask you, but it may or may not exist anymore. I'm not 100% sure if it does. It did up until about 2 years ago. They may have withdrawn it from the market. I'd have to Google that up afterwards but to be 100% sure. TDK, Teddy doesn't know anymore. Okay, so you have other things that can take place in digital hearing aids. You can have what's called feedback reduction. Automatic feedback reduction. This is kind of cool too. Look what causes feedback in a hearing aid. Now here's an output frequency response of a fictitious hearing aid. Okay, the horizontal is frequency, the vertical is dBSPL, or here I'm calling it gain. Okay, but the point is, here you go. You've got a peak. And it's this high frequency peak that might cause feedback. And so what you can do in a digital hearing aid is you can simply reduce the particular peak there to kind of get rid of the feedback. If you could, then you'd get rid of the feedback. Now, let's make sure we know what feedback is before we go any further. Feedback is the same thing as if you are talking in a mic and then you walk too close to the speaker and then you get that piercing shriek. That's because not only your voice is going into the mic, but also sound from the speaker is going into the mic because you've moved too close to the speaker. So you're getting a vicious loop, okay? The mic is amplifying the sound's coming, or it's changing the sound into electricity. The speaker's changing the electricity back into sound, but now it's entering the mic. You're getting a loop between the speaker and the mic. That's not what you want. You want your voice into the mic and the sound from the speaker coming out of the speaker. Okay, the only thing you want going in the speaker is your voice. You don't want the speaker sound entering into the mic. Otherwise, you're going to get feedback. And that's what it is in hearing aids. In hearing aids, what feeds back? High frequencies. Okay, not lows, highs. Why? Because highs bounce, lows bend. Remember that from way back in 110 acoustics? Low frequency waves are long. They're at least 1 foot long, 2 feet long, 3 feet long. A 250 hertz tone is 4.5 feet long. So that's not going to bounce off of anything. That's going to bend around things. Whereas 4,000 hertz, short. 8,000 hertz, even shorter. So those little waves are going to, they can't bend around heads. The head's too fat. Okay? They can barely bend around my finger. It's too wide. So they bounce. And as we said in 110, elephants emit low-frequency sounds that are so long, they'll bend around trees and over hills and down into valleys. Bats, on the other hand, emit extremely high-frequency sounds. Bats can't see very well, and they use the high-frequency sounds like radar, because the sound they emit bounces off the bug, and by picking up the bounced off sound, they know where to turn and where to catch the bug and eat. So low frequencies bend, highs bounce. So highs bounce, and they are the ones prone to cause feedback because they're going to bounce off the eardrum and leak out of the vent. They're going to bounce off the eardrum and leak around the sides of the hearing aid and get out and then get picked up by the mic. Amplified, bounce off the eardrum, leak out, get picked up by the mic. Feedback. Instead of just environmental sound coming into the mic. Now it's the amplified sound from the speaker, the receiver, being picked up by the mic. Same picture as if you talk into a mic and go too close to the speaker. Either one is going to create the high frequency shrill whistle. Feedback, of course, is your friend if you're trying to see if a hearing aid works. You're going to hold that guy in your hand and you're going to squeeze it. And if you can make it feed back, great. Then you know the hearing aid's working. Okay, but you don't want that occurring in the ear. So digital hearing aids have automatic digital feedback reduction. And it's quite cool what they do. There's various ways of doing it. We used to, in analog hearing aids, we used to use filters. And we'd put the filter in the ear hook. Now I wonder if I may still have an example of that. I might. I just very well might. Look at this. This is great. I can't believe I still have this. Wunderbar. I'm going to show you stuff. Stuff and things and stuff. Here you go. Perfect, perfect, perfect example. Here's an old analog hearing aid. Now look as I bring it closer. And maybe if I hold like a paper behind it, you'll be able to see it better. Look at that little gray thing stuck in the end of the ear hook. That's a filter. Okay? And if you could turn the filter toward you, it's a tiny little screen. You can't see it very well. My camera doesn't have the resolution, but trust me, what it is, if you were able to look at it dead on, you would see a tiny screen. That's why when wind blows through your screens, you hear kind of a the screen is acting like a filter. Do you remember when we studied in acoustics, impedance? And we said impedance equals resistance plus reactance. And what's resistance? Like simple friction. That's what a screen offers to sound going through. And resistance in any object is equal for all frequencies. And so filters in the end of an ear hook of a hearing aid are going to dampen the peaks in a frequency response wherever the peaks may be, because they are acting as resistors. Okay? What's reactance? Opposition due to mass, opposition due to stiffness. And remember, if you took that frown and turned it upside down, you had resonance, all that stuff from 110. Okay, well, analog hearing aids used filters. They used filters in order to get rid of the peaks in a frequency response. And what were those peaks? Much as I showed you here, sharing screen, looking at the PowerPoint, here's the peaks. And when you used a filter in a hearing aid, you were able to dampen all of these peaks. You get rid of them. So filters would smooth out the frequency response. That was the analog way of handling it. Okay? Most digital hearing aids today have automatic feedback reduction, and so we don't need to rely on filters, because filters, as in analog hearing aids, often got clogged up by debris, sweat coming up the tubing of the hearing aid. Okay? Sweat, moisture, whatever, crap coming up would plug up the filter. And then the filter would be plugged and the hearing aid was dead. So you'd have to completely replace the filter. It was easy to do, but it was a complete pain in the arse, because the hearing aid, the guy would be changing his battery and he'd be all freaked out because even the new battery wasn't working. It's because the filter was plugged. Okay, well, with automatic feedback reduction, you don't need to rely on the use of filters. The first kind were called static notch filters. They were the cheapest kind. Simply reduce the gain in a small frequency region. So much like this picture here, simply reduce the gain in a small frequency region, and you'll get rid of the feedback. Your notch filter could be here, it could be over here, it could be over here. It was usually in the highs at the frequencies where the feedback was occurring. But feedback can change. I mean, things can change in a hearing aid. So a static notch filter didn't always work all that well. If the feedback peaks were consistently at the same frequency, yeah, then they worked well. Relatively little battery drain due to small processing demands. Now think about this. Now you're going to get more complicated. Now you've gone up a step and you go to roving notch filters. So automatically your digital algorithms in your digital signal processor, let's go back to the slide here, in your digital signal processor, this has to do way more number crunching. Because not only are you fitting the hearing aid with the proper gain to match the demands of the audiogram and the fitting method that you chose, but now you're using automatic feedback reduction, and not only are you using static notch filters, you're using roving notch filters, which means that as these peaks may change, because now you're standing next to a fridge versus now you're standing next to a wall versus now you've got your hand because you're putting your hat on, any of those is going to cause feedback, right? You put your hand up close to an ear and any leaking sound is going to get picked up. You stand too close to a wall, you might get increased feedback there too because the sound's bouncing off the wall. So at any rate, roving notch filters could rove, they could move, and they could attack the feedback wherever the peaks occurred. Well, that requires a little bit more signal processing. Often a maximum of 3 roving notch filters was all that your battery and digital signal processor could handle. Then they got to phase cancellation, and that's the most common now. Now check this out. The hearing aid is going to be producing feedback at some particular frequency, and it's going to remember what that frequency was, and then the hearing aid itself is going to produce a sound of that very same frequency, but in opposite phase. 180 degrees phase. And so it's going to cancel it out. Phase cancellation. The sound of one hand clapping. Okay? Remember what you learned in acoustics. 2 sounds presented that are 180 degrees out of phase will cancel each other out. So if this is like 3,000 hertz, the hearing aid is going to sample that 3,000 hertz and it's going to flip it upside down and produce it again, or against it, against the feedback that's occurring. And now the feedback that's occurring at 3,000 hertz is canceled out. Feedback cancellation. And again, all of these things take more digital signal processing power. They demand more current from the battery. So the more sophisticated you get, the harder it is to handle all these things. So I'm hoping now you're kind of getting a grip of some of the complexities in the digital hearing aid world. And we've only scratched the surface. We've only touched the first half of Unit 5. Okay? We'll continue on this next week. But read phase cancellation. It's the most common now. The feedback peak is detected and reverted into opposite phase. It's done at the microphone stage. It's done at the microphone stage. Don't ask me how it's all done. I'm no engineer. All I know is if you're getting feedback at a certain frequency, the hearing aid is literally going to cancel it out by producing another tone that's equal but opposite in phase, and it will knock it out. Powerful tool, but requires more battery power. So now back up to the beginning. What have we covered so far today? We've talked about knowing your analog forebears and how hearing aids today are relying on fitting software. And that doesn't mean we're not nice people. It just means that without the fitting software, how the Sam Hill are you going to control all of the the gain, the compression, the directionality, the digital noise reduction, the feedback management in this channel. How are you going to do that in this channel and in this channel? The software handles it for you. But in a weird way, it's kind of like we've done a frontal lobotomy. I'd rather have a bottle in front of me than a frontal lobotomy, okay? In a weird way, we've lost some of our connection to the knowledge of compression in hearing aids because hearing aids are digital and the software does it all for you. So it's not as important to know what's actually going on underneath in terms of fitting the hearing aid. But as HIS grads from OTC, we need to have more than just that belief, the software will do it for you. No, no, no. Know your history of compression, know what output limiting is, and it's still used in digital hearing aids. Know what WDRC is, what it was, and it's still used in digital hearing aids today. So none of that's been thrown away because digital hearing aids today are imitations of their analog hearing aid characteristics of their forebears. Then we talked about the differences between analog and digital, and I gave you a whole spiel on records playing on a record player. Analog. Then we did a short history of some of the first digital hearing aids. Then we talked about, so lots of bands, many channels, that's one aspect. That's the first main aspect. The second one is feedback reduction. And what will we do next week? We're going to look at how was compression used in digital hearing aids? How is it presently used? And look, it's only this long. Look at that. It only needs to be a third of a page in length. How come? Because you've already studied compression. We don't need to redo the wheel. You've seen it already. All we're going to do is just talk about how it's implemented in today's digital hearing aids. So all that work you did prior to the midterm pays off in this section. And then we'll finish next week by talking a little bit about something called expansion. And expansion takes a little bit of explanation. We'll talk about it and what it is and what it's for and what it does. So digital solutions for two problems with WDRC. We'll finish next week talking about that. So this has essentially been about a 49, 50-minute Zoom session. Many of you probably didn't even know that the Zoom session was happening today. Doesn't matter. I'm going to email everybody and tell you that this just took place. Then hopefully you'll watch it. Okay, I will stop sharing screen and have you look at my ugly mug one more time. Isn't that neat? My whole little bag of hearing aids here. Good stuff to have. Very, very handy. A little baggie of hearing aids. All right, cool. I did 110 Zoom session, then a 120 Zoom session, then this one. I could take this thing out. All right, adios. Have a good time. I'll stop recording here.